Everybody see my screen, hopefully. Once again, when I am in presentation mode, I cannot see the chat. So if you have a question or if you cannot see something like a video or part of the presentation or something, speak up and shout at me, let me know, right? So today, we're going to be talking all about earthquake hazards. On the last time we went over what an earthquake is, basically, and the different ways we can measure an earthquake, figure out where the location is, figure out how big it is, all that kind of stuff, right? So today we're going to talk about the hazards associated with earthquakes, and what possible mitigation we can have against these hazards. And again, mitigation is a huge thing we'll be talking about in this unit of natural hazards. And then once again, mitigation being, how do we buffer against the effects, of say in this case an earthquake, and some of the hazards with earthquakes. How do we buffer against that as a society, so we can minimize the damage, the destruction, and of course the loss of life that occurs, right? So we'll be looking at the following things. First of all, one earthquake hazard obviously is ground shaking, right? That's a pretty obvious one. Landslides precipitated by all the ground shaking, that's another big one. Some earthquakes can launch thousands of landslides. Ground failure, foundation failure of buildings, that's another big hazard associated with earthquakes, right? We saw that in the video of Mexico City last time. And then ground rupture, changes in ground level. So, the ground can, or foundations can fail, right? Or they can rupture and change in ground level, or, sliding past, right? These, of course, are not going to be good, especially if you decided to build a building across that fault, right? Fires, right? Now, naturally, out in the middle of the woods, does an earthquake cause a fire? No, you don't get an earthquake and then trees and squirrels go bursting into flames. That just doesn't happen. However, in urban areas, when you puncture gas lines and gas mains and all that kind of stuff, and we have electricity going around, and you cut off water mains, those get ruptured, right? The fires is historically a big component of the damage that is caused by earthquakes, but of course only in cities, right? And then tsunamis, we'll talk tsunamis. Tsunami is the number one deadly earthquake hazard. And tsunami, of course, is a giant wave coming at you, generated by an earthquake. They can be generated by other things, but the largest, the most destructive tsunamis are generated by earthquakes. Right? And by the way, just as we're going forward in this natural hazard section, no matter what hazard we're talking about, whatever has to do with water is always the deadliest, right? So a little water may not have hurt anybody, but a lot of water has killed a lot of people. So here in earthquakes, it's tsunamis, right? When we talk volcanoes, it's lahars, which is a volcanic mudslide, right? And of course, floods, just in general, are the number one loss of life around the world. So tsunamis, will look into those, right? Let's start off with ground shaking, right? Again, just to remind you, the shear, the S waves, and the surface waves, or otherwise known as the L waves, these do by far the most damage. The P waves are just kind of, compression and extension, but the S waves, they're the ones that are going like this, and then the surface waves, going like that, and all sorts of weird stuff. So these are the ones that really cause a lot of damage, right? The actual movement of the ground is expressed as what's called base shear, which is a percentage of the acceleration due to gravity. So you can imagine if you have, large masses of rock and earth and stuff moving, sometimes during these earthquakes, they can move, faster than gravity. So that's called base shear. Yeah, I'll do that next time, right? So in intense ground shaking, what are some of the issues that it can cause? Buildings can deform from cube shapes to rhomb shapes, so going from cubic to rhombic, right? That's not good, right? They can shift off their foundations. And check out this building here, this apartment building, right? Basically what happened is this whole building just went ka-thump, 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 and then landed on top of all these cars. And now you have a, mobile apartment building, I guess, right? You can also suffer from what's called story shift and collapse. That's up here, right? It's a nice way of saying when you suddenly find your third floor apartment on the first floor, right? So these are some of the things that can happen during intense ground shaking, right? How do we mitigate against the ground shaking and the damage to buildings and stuff, right? Well, one of the ways we can do it is bolt the frame of the house to the foundation. So whoops, wrong button. We go back here, right? We look at this building. This building probably wasn't bolted to the foundation. So now, you know how your house is kind of built. We have our cement foundation that's built into the ground, right? And then your house is built on top of that, but you don't necessarily screw the actual wood part of the house to the cement foundation, because what's going to move a thousands of pound house or multi-ton house off of its foundation, right? Well, an earthquake is one of the things that can do that. So simply taking these little kind of stupid 50-cent little metal plates, and actually bolting one to the frame of the house and then bolting the other to the foundation, and doing that around the house a few different places. Those simple little stupid metal plates can help hold your house in place when the shaking starts, right? So you don't end up like these poor folks right here. All right. Building shear walls, right? So walls with a plywood sheeting nailed over top of the wood frame. So again, once you're building a house, right, you build up the frames, right? You got your studs 16 inches on center from each other, right? And then and then that wall's put up, and then you put insulation in it, and you put trim on the outside and all that. But and then on the inside you put what we call drywall made from gypsum, right? But there's that's pretty much it. So in areas where you've got a lot of a possibility of ground shaking from earthquakes, adding a sheet of plywood before you put in the drywall helps to just rigid up the whole structure. So if you think about it, you get one of those like really cheap bookcases or something like that, right? And you from the store, and you put it all together, and then the stupid thing's all wobbly until you put that little ridiculous cardboard piece on the back. You tack that on. Now all of a sudden it's a solid structure, right? That's the idea of putting in these plywood. So putting in the plywood before you put in the finishing, like the drywall of the house and stuff, just adds a additional level of shear strength to your house, right? And then diagonal bracing or blocking. So that's like here's your wall, and you just put a 2x4 or something on the outside to keep it from swaying and turning into a ROM essentially, right? Which is this, right? So that's kind of the best mitigation techniques against this ground shaking. And as I mentioned last time, building design, building codes, how you build in earthquake prone areas can have a massive impact on the amount of damage done, right? So places that have, and we saw that last time in Mexico City, places that don't have such great building codes, you get, even, 7.1 is a strong earthquake, right? But it was nothing compared to that 9.0 that we had in Japan. And notice what we saw in those videos were, just clouds of dust all over Mexico City from all the crumbling and collapsing structures. We did not see that, however, in Japan, even though that earthquake in Japan was, it was, instead of being a 7, it was a 9. So that is 100 times more ground shaking, but 900 times more energy release total. So here's another picture of another video of so this is another one of that 2011 earthquake in Japan, that 9.0. And this one, we're looking at two things. one thing I want you to notice as we look over the city, what we do not see again are all those clouds of dust like we saw in Mexico City, right? So we don't see those. And again, that a lot of that is to do with, you know, the strong building codes that they have in Japan for earthquakes. And another part of these building codes, you know, are, you know, I mean, it kind of sounds from an engineering standpoint, you know, almost kind of counterintuitive, but, you know, you want the buildings to be able to sway but hold together at the same time. So you want your buildings to have elastic potential, though, you know, the ability to move and bend, but then to snap back into their original position, right? So as we watch this video, we're looking for that. So first of all, notice not much. We don't see clouds of dust just rising up all over the city. But now as we turn to this building, right, this is not the camera moving, folks. This is the building moving. And of course, the building that the gentleman filming this in is also moving, right? So we're getting that kind of double motion, right? But could you imagine being on like the top floor of one of these buildings? I mean, that's moving just feet, right? I mean, right? Also, once again, during the earthquake in the background, not much moving. Here's going to zoom over to the right here so we can see this other building. That'll give us a really good idea. Now you can really see the sway of these buildings. And could you just imagine being on the top floor? I definitely would need a new pair of pants. Right. But looking into the background here, one thing we don't see again is you know, clouds of dust rising from falling buildings. Now they're going to pan over to the left and show us this big kind of long building, but we'll notice it's also doing the same thing. And of course, remember, these are designed to do this. This is, you know, how they are engineered to deal with all this vibration and ground shaking, right? So look at, even at this large building here, watch that thing move, right? Again, designed to do this, right? Once again, what we don't see in the background are lots of, you know, collapsing buildings. Right. Well, that's pretty cool. However, I should also point out, whoops. Stop. Okay, go away. I should also point out that it is not always the tallest buildings that are going to have the most swaying and the most shaking, right? It's not going to be the tallest buildings that are always the most susceptible to earthquakes or the most dangerous, right? It has to do more with a phenomenon called resonance frequency. So everything on this planet, you, me, you know, the bench, the cement, the, you know, bricks, the buildings, they all have this natural frequency that they want to vibrate at. And so when you have a tuning fork, right, and you hit that on something, it's vibrating its natural resonance frequency. Well, when you hit the resonance frequency of something, that's its natural wanting to vibrate, right? When you hit that, it can start to really create lots and lots more movement, right? So here's kind of the ultimate example of resonance frequency. What? There. I'll find one. We don't need it, but here we go. All right. So this is the Tacoma Narrows Bridge, going by Tacoma, Washington. Built back in the 50s, I believe. Did not last that long, and you'll about to see why here. But what happened to this bridge is the wind coming through this little narrow gorge here just so happened, even at like 35 or 40 miles an hour, so not even a very strong wind, happened to hit the natural resonance frequency of this bridge. Let's watch the results.
The Tacoma Narrows Bridge, dedicated in 1940, was the pride of the Northwest. Then the third longest suspension span that became known as Galloping Gertie, as it swayed in the winds sweeping up Puget Sound. 4 months after it was opened, those winds sent the bridge into a rhythmic dance of death. It literally shook itself to pieces. Caught in the middle of the bridge was a Tacoma newspaper man.
So this is all just being caused by a little 35, 40-mile-an-hour wind.
The bridge twists and sways in its death agony. Since its opening, engineers have studied ways to end its strange vibrations. They claim to be on the threshold of success, but too late. The reporter, Leonard Coatsworth, manages to fight his way to safety, most of the way on his hands and knees. He abandoned his car with a pet dog inside, the only life lost in the disaster. Giant cables are under stupendous strain as the great roadway of the bridge whips about like some fluttering ribbon. These pictures have been acclaimed as some of the greatest ever filmed. Here it goes.
Intense. Hopefully get the point on that one, right? So, not always the tallest building, right? That's going to be the most vulnerable. It's the building that, vibrates, that has its natural resonance frequency at the same frequency that the earthquake is vibrating at, or multiples thereof, right? So again, the Galloping Gertie just kind of gives us an example of, how even just a small force like that wind can generate, if you hit the right frequency, just massive effects, right? So we don't want to recreate Galloping Gertie again in either our roadways or in our buildings. So what are some things that we can do? So infrastructure, right? Like roadways, systems, right? Gas lines, water mains, all these things, right? These are going to be critical to recovery, right? Road systems are critical. If the roads are destroyed, you can't get help into the folks that need help, right? Basically it makes it a weak link for, or a very, dangerous spot for earthquakes, is if it destroys your infrastructure, then you have serious problems. You can't get help and can't move around and fix things, right? So as we saw last time in that video of Japan, right, those kind of columns of a roadway that was kind of moving and smashing back together, those were designed to do that, right? And here's kind of what they see. So roadways, you'll have natural break in them, right, between sections, and if it's going to move, right, in an earthquake, let it move, but then have things like, little hinges and cables to snap it back into its original place, right? So let it move with the earthquake, but make it snap back into its original position, right? We can also jacket columns with like a steel casing. That'll help some of the side-to-side wobble, right? We can wrap vertical support bars with rebar. So, inside these concrete columns, they have these vertical things of rebar. But then you can wrap another rebar around it, basically kind of like a slinky or a spring that's going to help move it back into that original position, right? And again, straps holding these joints together. Let the road move, but then let it, pull it back into the original position, right? So, and always, kind of the quandary of engineers is you got to build a structure that must be able to move and sway and hold together at the same time, right? Which does seem kind of like an engineering nightmare, but it's done very well, right? And then again, these, including building codes on how we build our infrastructure, is huge, right? The type of ground that you're building on can also have a big effect on these earthquake waves. So in solid rock, right, the earthquakes, the shaking that you're going to experience in an area that has solid rock from an earthquake, it's going to be shorter in duration and not as intense. However, when you get into like loose sediments like sand and gravel, or worst of all, soft muds, these soft sediments can move and prolong and actually amplify the ground shaking in that area. And from the very first picture I showed you at the very beginning, where that one bridge went down, in California, so a double-decker highway, it collapsed on top of itself. This is right where it happened. along this 880 here. And the reason it happened there likely was because this was a section that was built in the soft mud, which experienced a lot more ground shaking. And the supports for that double-decker highway were not engineered well enough to sustain the extra ground shaking that it experienced because of this soft mud, right? Next hazard, landslides, right? Thousands of landslides can be triggered by an individual earthquake. So the Northridge earthquake in California triggered almost 17,000 landslides, right? So this loose kind of sediment here, right? Here's one of them. All, they weren't all this large, of course, but this is a fairly large one. You can see this section of hill here, just kind of, from the vibration, was kind of on the edge anyway, and it just loosened up and slid down the hill. Now, you might feel pretty bad for these folks here, whose houses got buried by the landslide. That would be until you realize that all of these houses are built on series after series after series of former landslide deposits. So if you had taken a look at your geology, you would have known that these houses here maybe is not the best one to invest in because they are built on former landslide deposits. It means that in the future there will be another landslide, right? Mitigation, then avoid construction on steep slopes, unstable ground, right? And look at your geology, right? What are you building on? If it's a series of former landslide deposits, might not be the best place, right? Ground failure. So ground failing in those is areas where we get those soft sediments. Not only can it amplify and intensify the earthquake waves, it can also prolong them, right? But it also can cause the failure of the ground in what's something called liquefaction, where it basically liquefies the ground. So this is a real picture here on a street in California. This would have been a dirt road or dirt street. There's actually, if you look it up online, there's a whole series of these cars in this little cul-de-sac here that this happened to. But basically, what happens is during an earthquake, right, as you get the shaking, it starts to push water up into these soft soils and sediments, right? And that causes these sands then to be saturated and then partially supported by water, which really is no support at all. So the ground literally liquefies under your car or your vehicle or whatever, and then your vehicle sinks into it. But then when the shaking stops, right, now you've kind of like taking a bag of cereal or something and shaking it, right, it's eventually gonna kind of compact down to its lowest volume or consolidate. This will do work on this way on the ground as well, right, which means it becomes more efficiently packed. It occupies less volume, and it means that now not only is your car 3/4 buried in the ground, but it is going to be really hard to dig it out because this ground is more consolidated, more efficiently packed, and occupies less volume. In other words, it's denser than it was originally, right? So take a couple videos here. So here's liquefaction again. This is the Japan earthquake that we've been seeing lots of pictures of, right? So this water is all being pushed up in the crack in the ground, but it's basically just the whole area is being liquefacted, right? I could not find any videos of cars liquefying into the ground, but let's see here. Here's a good one. This is again from Japan.
Okay, we have earthquake right now. This is actually moving. See the cracks moving? That crack was not there. The whole earth is moving. I felt like I was drunk. I could see different parts. I could move. Wow. There was water.
So Well, we're looking over here. We're looking over this park. First notice, yeah, there's a little water. It's kind of pointing it out now, but, you know, it's pretty dry. We'll watch that change throughout this video.
Ground. Ground is just swaying right now. I don't know if you can see this on video. Crack is getting bigger and smaller, going back and forth.
Now,
water coming up all over.
Now we can see quite a bit more water up here, right? This is from liquefaction, not from burst pipes, but from liquefaction. The shaking of the ground forcing this water up, right? And partially supporting the sediment.
Park right now. Crack is just moving.
You see the water splashing up there now, right? Is it? Yeah.
This water was not there a minute ago. It's coming up different places. Here's coming up through the sidewalk. Buildings were making a racket. I seriously thought I was sick first because I didn't know what was going on. I could just feel like I was disoriented. Stepping over another crack.
Look at all that water out there now in the park, right? And he's about to tell us why the liquefaction is occurring in this area.
I wouldn't be surprised if the trains are not running anymore. I'm on the way to the train station. We've got a little lake, and here's a huge crack. It's still moving. It's just going back and forth, swaying. It's making me kind of nervous. Especially since this is reclaimed land that I'm on right now. This used to be part of Tokyo Bay. And they created this land by throwing landfill and mountains, rocks out here. And so this land could just go potentially. I don't know.
Okay, yeah, the land's not really just going to go, but that is why the liquefaction is occurring here. It's soft sediment. It is infill, right? They're creating new land in Tokyo Bay by, you know, pushing a bunch of dirt and rock and stuff to, you know, into the bay to create more, you know, habitable land. But that is why the liquefaction is occurring here.
People in the park, they don't seem too worried. They're not running away.
Mm-hmm. Well, we kind of get the point there. Giant sombrero, nice, right? So that is liquefaction. I got one more I want to show you here. Let's see here. Oh, I guess I didn't put it in here. Anyway, but yeah, that is liquefaction. But it can be much more devastating. A couple years ago, there was a whole about 10 city block area in Indonesia that got liquefact and all just kind of moved downhill. Let's see if I can find the video. I'll post that for you here. Again, what is liquefaction, right? Water's pushed kind of up and out of the overlying soils, building, you know, whatever's on top of it is then partially supported by water, which is, of course, no support at all. So those buildings, those cars, those whatever, right, you know, then collapse and sink into the ground. The shaking then stops and the ground re-solidifies, and now everything's stuck in the ground, right? So that is liquefaction, right? How do we prevent liquefaction? Again, know what you're building on, right? If you're building on very soft soils, you're going to need specialized foundations, specialized precautions, or maybe better even yet, don't build there, right?